Is Hervé Ménager. He is going to talk about use of the semantically annotated resources in Mobyle2 web framework.
Yes. Where's the pointer? Okay, thanks. Can you hear me? Yeah, okay. So, good morning. My name is Hervé Ménager. I work at the Institut Pasteur, and today I'm going to present you the work we're doing on Mobyle2 for using semantically annotated resources. So, for those of you who don't know what's Mobyle, it's a web-based workbench for bioinformatics. It's been developed by the Institut Pasteur and other collaborators since 2004, and it's currently in version 1.5.3. It's been developed with the goal of making it really easy for biologists to use, reducing as much as possible the initial learning curve, especially since many of them have very punctual needs for bioinformatics resources. Okay. Okay. So it also provides a persistent workspace if needed. And we are currently working on a new version of Mobyle, which is Mobyle2. So it's a major rewrite. It's currently in development, and it will include a set of new functionalities for collaboration, using groupware functionalities, for secure data sharing, a REST API, and one aspect, the one I'm going to be talking about today, is the use of ontologies to facilitate discovery and integration. So in Mobyle, you can access many different types of resources. The one on the left here is command line programs. You can also access web-based graphical interfaces that let you either visualize or edit your data. You can access workflows that let you automate complex tasks, and you can also share resources between different mobile servers, meaning that if someone who is running a mobile server shares one of the programs that he's running, another server can import it and directly publish it to its users. Then the programs will be directly executed on the publisher server. So it's a lightweight way of sharing bioinformatics resources. So to integrate resources in Mobyle, what you need to do is to write an XML file. This XML file includes many different informations, such as the name of the program, its authors, the publication associated, and also some information which is used for discovery and integration. The category tag that is used for the classification, and the parameters typing information for each parameter. So in the user interface, the category tags are used on the left to generate a tree view-based visualization. And the parameters typing is used, for instance, on the upper right corner for guiding interactive chainings. Here you have a user that generated a multiple sequence alignment, and he has a list of suggested services to directly chain this result to a compatible program for further analysis. And it's also used for format detection and conversion. When a user provide some data, we can detect the program using some plugins, detect the format of the data using some plugins, and automatically convert it to the accepted format for the program that is going to be used. The typing system that we are relying on for mobile is based on two main informations: the data type, which is the kind of information stored in the data. So a data type is either a reference to a Python class, for instance a sequence, or a dynamic subclass, which is used in the case where you don't want to be able to pipe it to everything that is in the superclass. So for instance, blast report is a subclass of report, but we don't have a class, a Python class for report. And we also have some data format information that specifies the format of the data or the format of the accepted of the accepted formats for the parameter. And all of these are basically strings. So the problem with this approach is that everything is freely extendable, and it led us to many annotation errors, especially with the people that installed mobile server on their own and did not really consult with us at any time. So for instance, if you have someone that uses the PDB, some PDB data, some of them used all uppercase strings, and some of them used capitalized strings, and this just doesn't work. And you also have problems of inconsistencies between multiple mobile net sites. You also have some confusion between data types and data formats. And finally, there's the problem that using this mobile-specific mechanism makes it really hard to share and reuse these annotations with other projects. So that's why we decided for the next major version of Mobile to use an ontology, because it's controlled and because it describes the relationships between different terms. And the scope of the ontology that we wanted to find would be an ontology that would define for the data and the parameters the type of information that was described and the format, and for the services classification, the hierarchy of categories that we were using as free strings. So that's where we found the embrace data and methods ontology, the EDAM ontology that some of you may already know. So this ontology has four main categories. The topic ontology describes subfields of bioinformatics. The operation describes a specific function that has a set of inputs and outputs for a bioinformatics method. The data axis describes a type of data such as sequence or protein structure. The format describes actually the format that is used to store the information. So to give you an example, a very simplified example, that's an example of the annotation of the MAFT multiple alignment program. So MAFT is annotated with the topic sequence alignment. It's an operation that's multiple sequence alignment construction. It has its main input is a set of sequences, and its main output is sequence alignment. and the format of its input and output, for instance, here are FASTA. I just put this to simplify the example. Okay, so as a result, we are using this information in the user interface of Mobyle to generate the tree-view hierarchy of that is navigated by the user for service discovery. So here we are using the IDAM topics hierarchy, which seems to be the more adapted way of showing all the list of the programs available. We also use this to guide users in the chaining of data and the reuse of data. Okay, they can the compatibility between existing data and results is based on the compatibility using the data and format axis of IDAM. We can augment these capabilities by providing more implicit workflow construction. Here, for instance, the DNA dist program from the Phylip package does not accept FASTA multiple sequence alignment. But since we have in the list of available services file reformatting operations that can handle the conversion between FASTA and Phylip format, we can actually suggest the use of the DNA dist and then at runtime actually execute a workflow that will first perform file reformatting and then the distance matrix construction. Similarly, we can we can help users build predefined workflows by letting them select the same operation, but then explicitly adding the file conversion steps in the workflow diagram when they are building a predefined workflow. We can also use this kind of information for automatic format detection when we don't know the format of the data that is provided by a user. Then we can automatically add first file format detection, then a file reformatting step. Similarly, if we have two consecutive steps in a workflow that cannot be directly chained because the following step only cannot handle a list of items that is produced by the first step, we can use a splitting strategy for automatic iteration over the data provided by the first step, and that can also be used for performance optimization by running in parallel the second step. We can also help people with the discovery of equivalent methods. For instance, here for let's say that a user has added a multiple sequence alignment operation to an example workflow. He can then change the actual operation, the actual program that will perform this multiple sequence alignment in the workflow editor just by selecting an equivalent program that has the same operation annotation, which is multiple sequence alignment construction. And we also let them build workflows with completely abstract methods. They can, at build time, just add a multiple sequence alignment construction step and then ask from the user at runtime that he selects in the actual program that is going to be used. So, in conclusion, Mobyle2 is still in development stage, but we think that ontologies are a useful resource for the integration of bioinformatics resources, especially for service discovery, for the implementation of high-level services, and for sharing resource descriptions, with other projects. The remaining challenges are the integration of ontologies, which are notoriously very complex in user-friendly interfaces, and addressing the quality of the annotations in service descriptions. Finally, I just want to thank the Mobyle1 and Mobyle2 development teams, our users, the contributors and authors of IDAM and tool registry teams, including Jonathan Matushkalas and Christopher Rapaki, and also the Mastodon initiative that funded our meetings. Thank you.
Questions?
So this is great, and as a tool author, I kind of always think about the work it's going to take me to integrate with a new platform. Briefly, why was a new platform created over the existing ones like Galaxy and others?
We took some different directions in some of the technical layers, such as the execution of the programs. We also have different ways of generating the user interface and displaying the results. But of course, we are open to any kind of collaboration.
So at the CodeFest, groups start talking about a standard way for the tools to describe themselves to ease this integration amongst multiple platforms. So I don't know if you saw that slide in this morning's summary of the CodeFest, but yeah. I'll make connections.
Yeah, that would be great.
So more sharing, more commonality would help out the rest.
That's exactly the point, actually. And I mean, it's beyond workbenches. It goes to tool registries, to provenance, to in many directions, actually, this kind of problem. Thank you.
Gilmar?